right, welcome back. Just picking up where we left off, proving the sine rule, and then we'll prove the cosine rule. So proving the sine rule, the derivative with respect to the sine. So that means that's the limit as delta x approaches 0 of sine of x plus delta x minus sine x over delta x. And remember the sum and difference rules, right? So that's the limit as the change in x approaches 0 of sine x cosine delta x plus cosine x sine delta x minus sine x all over delta x. Then that means we have the limit as the change in x approaches 0 of cosine x sine delta x. And notice we're going to use the limit rule, so we want sine of delta x over x because that's one limit rule that we learned last chapter, and also 1 minus cosine over cosine x over x. So if we can factor out 1 minus cosine, which we can from taking, so we took this part is here, so if we take the sine x out, negative sine x out here, then we're left with, so to take out negative sine x here, we have 1 and then minus cosine delta x all over delta x. So then we can split those up. So we have the limit as cosine times sine delta x over x minus the limit minus sine x times 1 minus cosine delta x over x, over delta x, sorry. So if you take those limits individually, you get the cosine x times 1, because remember the limit as x approaches 0 of sine x over x is 1, minus sine x times 0, because that's the limit of 1 minus cosine delta x over delta x. So that's just equal to cosine x. All right, you can do the same thing for the cosine rule. So you take the derivative with respect to x of cosine x, and that's equal to the limit of delta x as it approaches 0 of cosine x plus delta x minus cosine x all over delta x. So applying the sum and difference formulas, cosine x cosine delta x minus sine x sine delta x minus cosine x all over delta x. And then we can split this up. So notice here we have minus sine x times sine delta x over x. And then we have minus, if we take out the negative cosine, we have 1 minus cosine over delta x. And so it's equal to negative sine times 1 minus cosine times 0. So that's where you get negative sine for the derivative. All right, so here's some problems to build on what we've done so far. Find the equation of a tangent line to the function 2x to the third minus 3x plus 5 when x equals certain numbers. So first of all, when x equals -2, we know f of -2 is equal to -5 when we put it into the function here. So then we also know that f prime of x, when we take the derivative, well, that's going to give us 6x squared minus 3, because 5 is a constant, so it goes away. So that means f prime of -2 is equal to 21. So therefore, our equation is going to be y, because we're going to use the point -2, -5. So it's going to be y plus 5 equals 21 times x plus 2. So that's for -2. Now when we're talking about 0, well, f of 0 is 5, so that means the point 0, 5. F prime of 0 is -3, so it's y minus 5 equals -3 times x minus 0, which is just y minus 5 equals -3x. And last but not least, when x equals 2, f of 2, when we put 2 in, will give us 15. And f prime of 2, well, 6 times 2 squared minus 3, so that gives us 21. So it's going to be y minus 15 equals 21 times x minus 2. All right, so there's your answers there. Go ahead and try the next one on your own, and I'll show you the answers. All right, so there are the answers when you find the equation of a tangent line. You have to find the points, so 0, 0 is the first point, and then the slope when you take the derivative at that certain point. So the first one is y equals 3x, and then the second one you'll see here, because you get the point pi over 6, 3/2, and you get the slope of 3 rad 3 over 2. All right, so now we're going to start talking about rates of change, word problems. The first function that you probably are familiar with with physics and stuff like that is the position function. That is s of t equals 1/2 g times t squared plus v sub 0 t plus s sub 0. S sub t is the position function, where g is equal to, it depends, it's -32 feet per second if it's in feet, or it's -9.8 meters per second. V sub 0 is the initial velocity. And S sub 0 is the initial position. Or some people like to say the height. And t equals the time in seconds. Now, if it gives you a velocity between 2 points in time, if it says like find the average velocity of an object from one point to the other, so this is the change in position over the change in time, or in words, change in position. Over change in time. Which you could also write as S of B minus S of A over B minus A. And that's the average velocity of an object from A to B. right? So that tells us the average change from one point in time to another of the velocity. V sub t is equal to the derivative of the position. So the velocity is the derivative of the position. It's called the velocity function. And it represents the instantaneous velocity of an object. And that's also the limit as the change in t approaches 0 of s of t plus delta t minus s of t all over delta t. All right, because it's derivative of the position. The acceleration, that is the derivative of the velocity. That's also the second derivative of the position, meaning basically you took the derivative of the position twice, and it's called the acceleration function. And that is basically the change in velocity over time. So if we look at some of these problems here, so first, a pigeon on the ledge of the roof of a 500-foot building accidentally drops a rock from its mouth. The rock plummets to the ground, smashing an ant. So it wants to determine these things, like, for example, the initial position is 500 feet. All right, the velocity, well, he's on the ledge of the roof. The rock hasn't moved yet initially, so there is no initial velocity. G is, because it's in feet, it's negative 32 feet per second. And so the S sub t, if we multiply 1/2 times negative 32, we get negative 16 t squared. We do not have any velocity, but we do have an initial position of 500. So then it says find the height of the rock at specific points. So S sub 1. So we put in 1, square it, multiply it by negative 16, add 500, and we get 484 feet. And then at 3 seconds, we get 356 feet. And then at 5 seconds, we get 100 feet. All right, so then it says, what time will the rock squash the ant? So that means, when will the position hit the ground? So when will the position equal 0? So you basically are finding the x-intercept. So when we solve this, and divide, you get t equals 5.590 seconds. So that's how long it'll take for the rock to squash the ant, hit the ground. All right, so then next it asks us for the average velocity on certain intervals, like for example from 1 to 3 seconds. So you remember you have to find, so you'd have to go s of 3 minus s of 1 over 3 minus 1. So that's going to give me 356 minus 484 over 3 minus 1, which, when you do that, gives you negative 128 over 2, which is negative 64 feet per second. Then from 3 to 5, so we go 100 minus 356 over 5 minus 3, and that gives us negative 128 feet per second. And from 1 to 5, when we do this, we get negative 96 feet per second. So that tells us the average velocity on those intervals, how fast the rock is dropping. So these values represent the average velocity during that time interval. So to find the velocity, you have to take the derivative of the position. So it's negative 32t, because negative 16t squared plus 500, the negative 16t squared becomes negative 32t, the 500 becomes 0. So to find the velocity at 1, it's negative 32. At 3, it's negative 96. And at 5, it's negative 160 feet per second. So that's telling you at the specific point in time what is the velocity of the object. So that represents the instantaneous velocity of the rock at a certain time. So it's specific. Now the acceleration, remember the acceleration is the derivative of the velocity, so that's just going to be negative 32. So no matter what, it's equal to negative 32 feet per second. And that represents the rate of change of the velocity over time, or the acceleration. But that's just the average rate of change of the velocity. And if you look at the intervals above here, if you notice, each interval, the velocity goes up by 32, or drops by 32 feet per second. So how fast will the rock be traveling when it hits the ant? Well, that means you want to find v of 5.59, which gives you negative 32 times 5.590, which equals negative 178.88 feet per second. That's how fast it will be traveling when it hits the ant, poorly squishing it. All right, so that concludes part 2. Hope you enjoyed the videos, and I will see you guys in class. Have a good rest of the evening.